So let's continue with chapter 3. Now, I know this is getting to be a long chapter and it seems like we're talking about a bunch of random things, but we're still kind of setting the stage for a lot of what we're going to do later. So in Learning Objective 5, we're going to talk about location. So really location of where the data is falling in relation to the other data. So where a particular data point is falling in relation to the other data. So there's two things that we're going to look at. The first one is called Chebyshev's theorem. I believe that's how you pronounce that. My Russian is not very good, so if I'm pronouncing it incorrectly and you know how to pronounce that, then, please let me know, but I believe it's Chebyshev's. Now, the key with Chebyshev's theorem is that it can be used with any kind of data. So we've talked before a little bit about data that is normally distributed, meaning that kind of bell curve that we've looked at. We'll talk about that a whole lot more in chapter 6 also. So we're going to come back and talk about that a lot more. But Chebyshev's theorem can be used with data that is normally distributed and data that is not normally distributed. So we can find where a particular observation lies, the proportion of observations that lie within a certain number of standard deviations from the mean, where K is representing in that formula the number of standard deviations that we're looking at. So for example, we may say, well, how many data items fall within 2 standard deviations of the mean? We can use his theorem to calculate that. So let's consider that we have a class with 280 students in it, and they all take a test, and the average score, the mean score, is a 74, and the standard deviation is 8. So if we wanted to see what are the scores within, or how many students scored within 2 standard deviations, so we just picked 2 because that's kind of a normal one. So we would say 74 minus 16. 74 minus 16 is 2 standard deviations away. So 74 minus 16 gives us 58 as the lower bound, and 74 plus 16 gives us 90 as the upper bound. So we're asking how many students scored within 58 to 90 on the test. So in our formula then, K is 2 because K is 2 standard deviations. So when we plug this into our formula, we're going to say 1 minus 1 divided by 2 squared. And so that gives us 0.75. So 75% of the class scored between a 58 and a 90, or 75% of the class scored within 2 standard deviations of the mean. So if we look at the class's 280 students and 75% of them scored within 2 standard deviations of the mean, then that means 210 students out of the 280 scored between a 58 and a 90, right? So, this again, so almost 75%, we could say, passed the class or passed the test or did better. Now, granted, a 58 isn't necessarily passing, but it's close to passing. Now, the empirical rule is very similar, except that the empirical rule can only be used when data is normally distributed, when it has that bell curve as we see laid out for us here. So Chebyshev's can be used on any data. The empirical rule, we have to look at the histogram first to make sure that it is a normal distribution, that it is a bell curve. So the empirical rule tells us that approximately, and again, it's a little off, approximately 68% of the data of any observation will fall within 1 standard deviation of the mean. Approximately 95% of all observations will fall within 2 standard deviations of the mean, and approximately 100% or all of the observations will fall within 3 standard deviations of the mean. So we looked earlier at using box plots to help us determine if there are outliers, but we can also use the empirical rule or even Chevyshev's rule if it's normally distributed data to determine if there are major outliers here. Because if we're seeing something more than 3 standard deviations away from the mean, that's going to indicate that that's an outlier for us. So comparing the two, again, the main difference is that Chevyshevs can be used for any distribution. The empirical rule can only be used for a normal distribution. Now, Chevyshevs is what we consider a little conservative. It gives us a little smaller kind of tends to lower bounds. So if the data is normally distributed, we want to use the empirical rule. And if it's not, or we're not sure, if we don't know, then we want to use Chevyshevs. So let's compare, do that same analysis again, but using the empirical rule. So again, we've got a class with 280 students. The average score is 74. The standard deviation is 8. So this tells us that 68% of all students will score between an 82 and a 66. Okay, within one standard deviation away. So we can then know that approximately 95% of the students will score within 2 standard deviations, which we've already calculated as 58 to 90. So we know that 95% of the students will score within 2 standard deviations. Remember, Chevyshev's rule gave us approximately 75%, so that was a more conservative estimate. But since we know that this is normally distributed data, 95% is probably a better estimate. And then we know that, again, approximately 100% of the students will score within 3 standard deviations, so between a 94 and a 50. Excuse me, a 98 and a 50. So again, if we have someone who scores above a 98 or below a 50, then that's a clue to us that, hey, that's probably an outlier because the above 98, assuming the top score is 100, probably not, but someone scoring below a 50 in this case, in other words, more than 3 standard deviations away, would tell us that this is an outlier. Okay. Now, the last thing we're going to talk about in this set is the z-score. So the z-score, and we all use z-scores a lot. I'm just warning you now, we're going to come back and use these a lot. The z-score tells us for a given number, like for a given exam score, let's say, approximately how many standard deviations that is away from the mean. So oftentimes when we use a z-score, you'll see it written as standardizing the data. And that just means that we've kind of taken out, we're just reporting where the location to the mean is, as opposed to reporting the raw score. So our formula for a z-score is x, which is your observation, minus the mean divided by the standard deviation. So if the observation is exactly equal to mean, then the z-score will be 0. If the observation is greater than the mean, then the z-score will be a positive number. It will be above 0. And if the observation is less than the mean, then it will be a negative score. So, for example, going back to our data, let's say that we have 2 classes now. We have an accounting class and a marketing class. And the average on the accounting test was a 74, and the average on the marketing test was a 78. The standard deviation for the accounting class was an 8, and the standard deviation for the accounting class was a 10. So we can see if you scored a 90 on both tests, what's your z-score? How did you score in relation to the mean? So if we calculate this, first of all, for the accounting test, we'll say your 90 is your test score minus the mean divided by the standard deviation. So you scored as a 90 within 2 standard deviations of the mean for the accounting class. But for the marketing class, a 90 minus a 78 divided by the standard deviation of 10 is only 1.2 standard deviations away from the mean. So the way to think about this is, let's say that you scored a 90 on both tests. Now, first of all, a 90 is a great grade, but you scored the same on both tests. But relatively speaking, you did better on the accounting test because you scored higher, more higher than the average. That's not proper English, but you scored 2 standard deviations away. So you were farther away from the mean on the positive side than you were in the marketing class. So in the marketing class, your score, while still very good, was closer to average, whereas in the accounting class, you were much more above average.